After centuries of watching substances combine, burn, and transform, chemists were left with deeper questions. What is matter really made of? Why do elements always combine in fixed ratios? Why is mass always conserved in reactions? The turning point came with one man, John Dalton, who proposed the first scientific model of the atom. His theory didn't just answer old questions, also it laid the foundation for everything modern chemistry would become. John Dalton, an English schoolteacher and chemist, published his groundbreaking theory in 1808 in a work titled A New System of Chemical Philosophy. Relying on experimental evidence, especially from the laws of chemical combination, he proposed something bolder, that all matter is made up of atoms, and these atoms combine in simple, predictable ways. This wasn't just an idea, it was a scientific model that explained the mysteries of matter. Let's now break down his atomic theory step by step. Dalton's atomic theory introduced 6 powerful postulates, each one revealing a fundamental truth about matter. First states that all matter is made of indivisible particles called atoms. At the time, atoms were believed to be solid and indestructible. Second says all atoms of a given element are identical, same mass, size, and chemical behavior. Third follows that atoms of different elements are fundamentally different in every measurable way. Fourth states that atoms combine in simple, whole number ratios to form compounds. Like water, H2O equals to 2 hydrogen atoms plus 1 oxygen atom. Fifth says that chemical reactions are simply rearrangements of atoms. No atoms are created. None are destroyed. They just shift partners. And the sixth states that in any compound, the types and numbers of atoms remain constant no matter how much you scale it up or where you find it. Dalton's theory transformed atoms from a philosophical idea into a scientific framework. Let's explore the remaining principles of Dalton's atomic theory. First, chemical reactions involve the rearrangement of atoms. No atoms are destroyed or created, they simply shift and form new combinations. Second, Dalton stated that atoms are neither created nor destroyed in a chemical reaction. This directly supports the law of conservation of mass. Third, every compound always contains fixed types and numbers of atoms. That means water is always H2O, never more, never less. Finally, Dalton transformed the atom from a philosophical idea into a scientific concept. His model gave chemistry a solid foundation based on measurable evidence. Dalton's atomic theory didn't just introduce new ideas, it explained the chemistry laws that had puzzled scientists for years. The law of conservation of mass. Dalton showed that atoms are never lost or gained in a reaction, they're simply rearranged. The law of definite proportions. His model explained that atoms always combine in fixed ratios to form compounds. The law of multiple proportions. It made sense once you realized atoms combine in countable, whole number units. In one stroke, Dalton unified all major chemical laws under a single atomic framework. Let's bring Dalton's atomic theory to life with a simple reaction. 2 molecules of hydrogen combine with 1 molecule of oxygen to form 2 molecules of water. What's happening here? First thing is no atoms are created. Second is none are destroyed. They're simply rearranged. This is Dalton's principle in action. Atoms are the building blocks of all matter and every chemical reaction. They shift, bond, and separate, but they remain intact. Dalton's atomic theory truly changed the game in chemistry. Here's why it was revolutionary. It explained the conservation of mass and fixed ratios in chemical reactions, something scientists had observed for centuries. It introduced a clear, mathematical logic to chemistry, making it a more exact science. It brought in the concept of chemical formulas and atomic level thinking, giving meaning to the symbols we use today. And for the first time, it offered a testable model of the atom, one that connected theory with experiment. Dalton gave chemistry structure, clarity, and a solid scientific foundation. Dalton's atomic model was groundbreaking, but as science progressed, its limitations became clear. Atoms aren't truly indivisible, they're made of electrons, protons, and neutrons. Not all atoms of an element are identical. Isotopes exist with different masses. Some compounds don't follow whole number ratios, especially in complex structures. And Dalton's theory couldn't explain chemical bonding or molecular structure. But despite these gaps, Dalton's theory was the first step toward a deeper atomic understanding. It laid the foundation on which modern atomic theory was built, a legacy that still shapes chemistry today. Dalton didn't get everything right, but he gave chemistry something it had never had before: a scientific model of the atom. He showed that matter behaves logically because it's made of logical, countable units, atoms. His atomic theory became the launchpad for everything that followed, from the discovery of electrons to the rise of quantum chemistry. And now, we move a step further. In the next lesson, we'll explore atomic mass and molecular mass and learn how chemists measure the invisible building blocks of matter.